In this scenario, we have this hanging sign, and like the last one, it's in equilibrium. And so what we might see then is that this angle 2, if we call this tension 1, and this, we'll call this tension 2, and this tension 1, this tension 2 will have a vertical component and a horizontal component. And A1 will have a vertical component and a horizontal component. And of course, there's a force of gravity in this direction. So pulling this out and drawing it, we've got force of gravity, and we have Ft1z and Ft2z. You see, this body is not accelerating vertically, so the vertical forces, these two, must balance this. So Ft2z plus Ft1z must equal Fg. And then the similar thing is happening in the horizontal. We have Ft1x and Ft2x. The system is not accelerating in the horizontal, so these two forces must be equal and opposite to each other. And so conceptually, that's really what's critical in a problem like this. Now, laying out the algebra for it and all the variables, we can do the vertical. Fz. And so the net force is the sum of the forces, and that's Ma. And in the vertical, we have Fg plus Ft1z plus Ft2z. And the acceleration is 0. So that means Ft2z is equal and opposite to the force of gravity plus, oops, I misspoke. That's 0. And so the force of gravity is equal and opposite to Ft1z plus Ft2z. Such that if the force of gravity were, let's say, minus 80, and then this could be 30, and this could be 50. So minus of a minus 80 would equal 30 plus 50. So 80 equals 30 plus 50. We see how that would work. We don't know if it's 30 and 50, but we're just showing that the signs work. And now if we look at the force in the horizontal, well, we have the net force is the sum of the forces. Ma is Ft2x plus Ft1x. The acceleration is 0. So therefore, Ft2x is equal and opposite to Ft1x. So if this is 14 and minus 14, we have minus 14 equals minus of a positive 14, and they're equal to each other. And of course, we would go through the steps of using sine and cosine to figure out all those numbers. And in this scenario, given that there's 8 kilograms, well, 8 kilograms, that would factor into this Fg. So we would know this Fg, which happens to be minus 80. And then we would know that these two must add up to 80. Now, we don't know what alpha or alpha 1 or alpha 2 are, but we would know in a problem that we would be given. So the next question we have is to investigate here, what happens if alpha 1 goes to 0? So what if we keep taking this string right here and pulling it farther and farther and further and further in this direction so the angle decreases? Now let's see what effect that has. In doing that, it makes Ft1x increase. We know the dimension gets larger. And if we look at ft1z, what happens? Well, as we make that angle smaller and smaller and smaller, this overall tension has to get larger for this to stay the same. If this were saying 50 and this is 30, and I change that angle, this overall force is going to have to get larger and larger to keep this vertical up. And that's going to get larger as well, which makes the overall force get larger. So as we make that angle smaller and smaller and smaller, ftx gets larger and larger and larger. ft1z has to stay the same size. And so for ft1z to stay the same size, the overall ft has to get larger and larger and larger. When the angle goes to 0, then that would imply that the tension, this force, has to be infinity, which is just simply not possible. So the bottom line is, it's not possible to make this angle go to 0. It's not possible to make alpha 1 go to 0.